Hello. Until about 3 decades ago, quantum chemistry calculations were the prerogative of professional quantum chemists like me because the computational requirements for configuration interaction and coupled cluster calculations scaled with the fourth power of the number of electrons. That is, so as the number of electrons in a system increased, the computational requirements became prohibitive. As a result, such accurate calculations were possible only for the very smallest of molecules and not for the kinds of molecules that chemists were interested in. That situation changed with the advancements in density functional theory, which avoids the use of the wave function psi and the wide availability with the wide availability of density functional theory codes. And that's what we shall now talk about. So we know that the electronic energy is given by the sum of the kinetic energy of the electrons, the potential energy of electron nuclear attraction, which we call Vn and E, and henceforth we shall just call V, capital V, and the potential energy of interelectronic repulsion, which we have called VEE until now, and shall henceforth just call U. The kinetic energy of the electrons, T, is given by minus half sigma I del I squared gamma, where gamma is the 1 RDM or the 1 electron reduced density matrix. Capital V, the potential energy of electron nuclear attraction, is given by minus sigma alpha sigma I integral d tau I z alpha rho of R by Ri alpha, which can also be written as integral d tau V of R rho of R, where rho of R is the electron density and V of R, small v of R, is known as the external potential, and for a molecular system that is just given by this formula. But in general it can also include the effect of potentials which interact with external potentials which interact with the electronic charge, such as an external electric field or the field of radiation. Okay. And the potential energy of interelectronic repulsion, U, is given by this formula in terms of the pair density gamma of Ri and Rj. So we see that to calculate the energy, you don't need the wave function at all. All you need is the 1 RDM, the electron density, which can be obtained from the 1 RDM, and the pair density, which can be obtained from the 2 RDM. So, and since the 1 RDM can also be obtained from the 2 RDM, so all you need is the 2 RDM, the 2 electron reduced density matrix. But actually, the situation is even simpler than that. And in fact, the 1 electron density, rho of R, is sufficient to determine all ground state properties. This general result was shown by Walter Kohn and his student Pierre Hohenberg in 1964. Before introducing density functional theory, let me mention Kato's theorem, which defines the cusp condition on the electron density at the positions of the nuclei. That is, the slope of the electron density at the nucleus is related to the nuclear charge and the electron density at the nucleus. Thus, the slope of the electron density at the nucleus is determined by the atomic number of the nucleus. Bright-Wilson observed that this provides an explicit procedure for constructing the Hamiltonian of a Coulomb system from the electron density, since the cusps of the electron density tell us where the nuclei are from R alpha and what the nuclei are from Z alpha. And the integral of the density determines the total number of electrons, since n equal to integral rho of R d tau. Therefore, the electron density rho of R is actually all that we need. Okay. Thus, the electron density rho of R, which is equal to psi star of R1 R total Rn times psi of R1 R total Rn, integrated over the coordinates of all but one electron, that is integrated over dr2 till drn, contains all the information about the ground state. Since rho of r is a function of only three variables x, y and z, this represents a great computational simplification, since instead of dealing with the many electron wave function, which is a function of the coordinates of all the electrons in the molecule, we only have to deal with the electron density, which is a function of just x, y and z. Walter Kohn proved that the external potential V of r is determined within a trivial additive constant by the electron density rho of r. Since rho of r determines the number of electrons, that is n equal to integral rho of r d tau, it follows that rho of r also uniquely determines the ground state wave function, the ground state electron density E, the molecular structure and all other electronic properties of the molecule. So according to the Hohenberg-Kohn theorem, rho of r determines V of r, which in turn determines capital V, since the expectation value of capital V is just integral d tau small v of r times rho of r. And rho of r determines n, since n is just integral rho of r d tau. Further, since v and n together determine the Hamiltonian, since h is equal to t plus v plus u, and knowing h, we can solve the Schrodinger equation, that is, we can diagonalize the Hamiltonian to determine psi. Therefore, knowing v and n, we can determine psi, or in other words, knowing rho, we can determine psi. But we already know that the electron density can be obtained from the many electron wave function by integration. That is, rho of r equals integral psi star psi over d tau 2 till d tau n. That is, knowing psi, we can determine rho of r. But from the Hohenberg-Kohn theorem, we know that rho of r determines small v of r and n, and which in turn determines h, which determines psi. That means rho determines psi and psi determines rho. That means there is a one-to-one mapping between the many electron wave function and the one electron density. The formal proof of the Hohenberg-Kohn theorem proceeds by reductio ad absurdum. That is, assume that the Hohenberg-Kohn theorem is not true. That means assume that there exists another potential V dash of r, which corresponds to the ground state wave function psi dash, that gives rise to the same electron density rho of r as given by the potential V of r, which corresponds to the ground state wave function psi. Then, except in the case where V of r minus V dash of r is a constant, we must have psi dash equal to psi, since they satisfy different Schrodinger equations. That is, E is the expectation value of the Hamiltonian h with the wave function psi, and E dash is the expectation value of the Hamiltonian h dash with the wave function psi dash, and we have assumed that the ground states are non-degenerate. That means there can exist only one wave function with a given energy. Here, E and E dash are the respective ground state energies of the electronic Hamiltonians h and h dash, where h is equal to t plus v plus u and h dash equal to t plus v dash plus u, and where expectation value of v is equal to integral v of r rho of r d tau, and expectation value of v dash is equal to integral v dash of r rho of r d tau. From the variational theorem for the Hamiltonian h dash, we know that E dash, which is the expectation value of h dash with the wave function psi dash, has to be less than the expectation value of h dash with some other wave function psi, and the right hand side can be written as bra psi h plus v dash minus v psi ket. But bra psi h psi ket is just E, and therefore E dash has to be less than E plus integral V dash of R minus V of R times rho of R d tau. Similarly, from the variational theorem for the Hamiltonian H, we know that E, which is the expectation value of the Hamiltonian H with the wave function psi, has to be less than the expectation value of H with some other wave function psi dash, and this right hand side can now be written as bra psi dash H dash plus V minus V dash times psi dash ket. But again, psi dash H dash psi dash is equal to E dash, and therefore E has to be less than E dash plus integral V of R minus V dash of R times rho of R d tau. Adding these two equations, we see that the terms under the integrals cancel out, so we have the inconsistency E plus E dash is less than E dash plus E. That obviously cannot be true, and therefore the original presumption was in error. In other words, the V of R and V dash of R can differ by at most a trivial constant. Okay? If V of R and V dash of R differ by more than a constant, they cannot be associated with the same electron density. In other words, V of R and thus the Hamiltonian H are unique functionals of the electron density rho of R. So what is a functional? While a function depends on one or more variables, we can say very simply, and avoiding complications, that a functional is a function of a function. The electron density is a function of the variables x, y, and z. So something which depends upon the electron density is a functional. Thus the energy functional E of rho of R is a functional of the electron density function. Hohenberg and Kohn then proved a variational principle for the energy functional E of rho of R, which is known as the second Hohenberg-Kohn theorem. That is, for a trial density rho dash of R, which is everywhere greater than or equal to 0 and which integrates to the total number of electrons n, the true ground state energy E0 is a lower bound for the energy generated from this trial density rho dash of R. That is, E0 is always less than or equal to E of rho dash of R. So what is this energy functional E of rho of R that we have been talking about? Unfortunately, no one knows. Okay. The first Hohenberg-Kohn theorem is an existence proof. It guarantees the existence of such a functional, but it does not specify its form. The second Hohenberg-Kohn theorem is a variational principle for the density analogous to the variational principle for the wave function. It guarantees that the energy generated by this functional will be minimum for the true density, but again it does not specify what the functional is going to be. Finding the Hohenberg-Kohn energy functional E of rho of R has been the holy grail of density functional theory. So in accordance with the second Hohenberg-Kohn theorem, we minimize the energy with respect to arbitrary variations in the electron density, but subject to the normalization constraint, that is, that integral rho of R d tau is equal to n. And that can be done by introducing a Lagrange multiplier mu, which leads to this equation. Here, mu is known as the chemical potential. It is the Lagrange multiplier for the normalization constraint on the electron density, that is n equals integral rho of R d tau. This leads to the Euler-Lagrange equation, that is mu equals delta E of rho of R by delta rho of R. Here, the chemical potential mu is the functional derivative of the energy functional with respect to the electron density. Why do we call it the chemical potential? Well, let us look at the analogy between density functional theory and chemical thermodynamics. In thermodynamics, the free energy G is equal to sigma I Ni mu I, where Ni is the number of moles of component I, and is also equal to E plus PV minus Ts. Thus, the chemical potential mu I is the free energy per mole of component I. Then we also have dG equals VdP minus SdT plus sigma I mu I dNi. And with Maxwell's relations, that is del G by del P at constant T and Ni equals V, and del G by del T at constant P and Ni equals minus S, we can write dG equals del G by del P at constant T and Ni dP plus del G by del T at constant P and Ni dt plus sigma I del G by del Ni at constant T, P and Nj not equal to I dNi. Thus, the chemical potential mu I is equal to del G by del Ni at constant T, P and Nj not equal to I. In density functional theory, let us write the energy functional as a functional of rho of r and v of r, pretending that we can vary rho and v independently. Then E is equal to f of rho plus integral v of r rho of r d tau, where f of rho includes both the kinetic energy and the interelectronic repulsion, and is thus a universal functional of the electron density. That is, it has the same form for all molecules, atoms, ions, crystals, and so forth. But if we can vary rho and v independently, then for any change in the energy dE, we can write dE equal to integral delta E by delta rho at constant v times delta rho of r d tau plus integral delta E by delta v at constant rho times delta v of r d tau, which is equal to integral mu delta rho of r d tau plus integral rho of r delta v of r d tau, where the chemical potential mu is the functional derivative of the energy functional with respect to the electron density. The functional derivative of the energy with respect to the external potential is just the density itself, because the only term in this equation which depends upon v of r is the second term, whose functional derivative is rho of r. From this formula, Parr, Donnelly, Levi and Palke identified the electronegativity as the negative of the chemical potential. That is, the electronegativity chi is equal to minus mu, which is equal to minus del E by del N at constant V, which is approximately half I plus A, where I is ionization energy and A is the electron affinity. So, if we can pretend that the energy of an atom or molecule varies continuously with the number of electrons, then this is the neutral atom or molecule, and this is the energy of the neutral. This is the anion with Z plus 1 electrons and the energy of the anion. This is the cation with Z minus 1 electrons, and that is the energy of the cation. Then the taking the finite difference derivative of the energy on the right, we get the electron affinity, and taking the finite difference derivative on the left, we get the ionization energy. Thus, the electronegativity is the average of the ionization energy and the electron affinity, which is just Mulliken's electronegativity definition. Thus, Parr's electronegativity formula reduces to Mulliken's electronegativity definition in the finite difference approximation. Note that Parr's identification of the chemical potential as the negative of the electronegativity has been criticized, since the number of electrons n in an atom or molecule can only take on integral values and is not a continuous variable that we can differentiate with respect to. Taking the second functional derivative of the energy functional with respect to the electron density, or the functional derivative of the chemical potential with respect to the electron density gives us the chemical hardness or the homolumo gap or the band gap in solids. And this leads to a principle of maximum hardness during chemical reaction. The mixed second functional derivative of the energy functional gives us the Fukui function, which measures the propensity for chemical reactivity. Three kinds of Fukui function may be defined. The right finite difference derivative gives us F plus, which identifies the sites of nucleophilic attack in a molecule and is approximately the density of the lowest unoccupied molecular orbital. The left finite difference derivative gives us F minus, which identifies sites of electrophilic attack in a molecule and is approximately the density of the highest occupied molecular orbital. The average of these two gives us F0, which identifies sites of radical attack. Any density that is to be used in an energy functional must satisfy certain conditions, and these are that the density must be derivable from an antisymmetric wave function, which must be the ground state solution of the Schrödinger equation corresponding to some potential V of r. The first condition is known as the N representability condition, and the second condition is known as the V representability condition. In 1975, Gilbert showed that any positive density function which integrates to the total number of electrons and whose kinetic energy is finite can be derived from an antisymmetric wave function, thereby solving the N representability problem. V representability is in general not guaranteed by an arbitrary trial density. In his constraint search formalism, Mel Levi considered the functional f of rho that minimizes the expectation value of t plus u over all antisymmetric wave functions psi that yield that density rho. Then the ground state energy is obtained by minimizing f of rho plus integral v of r rho of r d tau, or minimizing the energy functional over all densities. In his book, Parr gives the example of trying to find out who is the tallest student in a school. Of course, you can ask all the students to line up in the assembly hall or the playground and find out who is the tallest student, but that runs into problems if even one student is absent on that particular day. Instead, the principal can ask all class teachers to line up to ask all the students in the class to stand up on a day that everybody is in that class is present and find out who is the tallest student in that particular class, and then ask all the class teachers to send that tallest student to the principal's office, and by lining up all those tallest students in the principal's office, you find out who is the tallest student in the entire school.